Perfect. And on Twitter as well? Perfect. Thank you so much. Okay, then let me share my screen and we can get started. Do you wait, sorry. This is where it should start. Okay, can you see my screen?
Yeah, we can.
Perfect. Yeah, then let's get going. Hi everyone. I'm Ansgar, co-hosting these research calls together with my colleague Barnaby, who is currently off for parental leave, and so I'll host today's call. We talked about different requirements for different types of nodes on the first research call, and for today's call, we wanted to zoom in on this specific quadrant here on our roadmap, the short-term focus for the execution layer, which is specifically about execution throughput scaling, which specifically also means that some of the other near-term topics for the execution layer will be out of scope for today's call, namely things like the future of EOF, if any, or account abstraction, topics like that will be out of scope. Also out of scope for this call will be statelessness. The schedule, basically, we'll have the main call split into two parts, part one and part two, 40 minutes each, with hopefully a little bit of time for discussion and Q&A after each part, and an intro at the beginning from Dankrad. And then we had some last minute kind of bonus additions, and to not make the rest of the call be too squeezed, we decided to basically have a bit of an overflow part at the end, so whoever can stay on for like 10, 20 minutes, 20 minutes afterwards, after the main 90 minutes of the call, we'll hear from Vitalik and Justin about the beyond the near-term vision, and then have a discussion that will be kicked off by Micah. So that's it for the housekeeping. Just already to mention it, we'll have the next research call probably on June 4th, which will focus most likely on ZK and statelessness, but that's not for today. So with that, let's get going. Dankrad, do you want to kick us off?
Sure. Wait, how do I share the screen here? Let's see. Okay, I can only share the whole one. All right. Can you see my screen?
Yes.
Yep. Cool. So I'll give a very quick intro on why scale the L1. I think I already tried to summarize my view on this in the recent post on ETH Magicians, but I'll try to visualize it a bit more here as well. So to start with, I think most people here are technical, and so I think the most important part of this is obviously if we could have scaled the L1 10 years ago, we would have done so. But this time is different. The tech is actually ready, or let's say at least very close to ready, so that on pretty short to medium term timescales, we can expect significant advances in our abilities to scale the L1 while remaining verifiable. And that's because ZK VMs with real-time provings are becoming available within the next few months. I say maybe second half of 2025. And then also Ethereum will have data availability sampling soon with PEERDAS. That's expected in the next hard fork. So that's hopefully within 6 months, at most within 12 months. And so this is everything that we need to verify a scaled L1. So once we have these, it's basically no longer a concern, can everyone actually follow the chain? And this brings us to thinking about what our node architecture should look like for the 2020s. When Ethereum was first designed, it was more like a 2000s node architecture, and that remained in the 2010s. And that's basically we put everything into this one little stateful node, and that fundamentally limits our scaling. And in the future, we can get the current and much better properties while even scaling by spreading out our node form factor and going on the one side to extremely lightweight stateless nodes that can even run inside user wallets easily. And on the other side, we will have a small number of nodes that are a bit more powerful and will be able to prove things or take special peer-to-peer roles. And then coming to more of the other side of the why, which is like one is, yeah, it's possible, but why should we do it, or why do we really need to like make it a big priority? One is if we just think even about the existing rollup centric roadmap, what we want is not the picture on the left where there's like a tiny L1 and then like very big powerful rollups. And there will be more on this why this is bad later, but like what we want is this powerful L1 and then many rollups that cluster around it. Because like on the left-hand side, at some point, those rollups might start thinking, okay, why am I a rollup here? Why am I not somewhere else or so? So like basically, it's not a very stable equilibrium, whereas the right-hand side can be much more of a stable equilibrium. The other thing is about fee revenue. So like at some point, I do believe that Ethereum will have to prove that it can raise a good amount of fee revenue. Like this is not about whether Ethereum should be purely valued on that, but it just makes Ethereum or Ether the asset strictly better if it can. And it makes it better if it can, even if it doesn't. So the one thing that we know is like contentious state on an execution layer with DeFi has an obvious mode. There's something that you can do on such an execution layer that you just cannot do somewhere else. Like if you want to access the liquidity that's on that layer, you can't go somewhere else and get that same liquidity. It's just not possible. Like for example, if you just want to send money, that's different because if you have money somewhere else, you can send it somewhere else. But like, yeah, so once you have this DeFi state, it has a fairly strong mode. And data availability, at least in its current form, does not have this mode. I think we can develop into something that has more of a mode, but like at the moment, the way that current rollups work, it has very little of a mode, which we can see because people simply like do change data availability sometimes. And like this indicates that it does not have a strong mode. So this means that the fees you can charge for this tend to be much lower. Like if you can just go somewhere else, then like when the fees get high, then you go somewhere else. But like if you can't, then you will pay the fee. So this indicates that an execution layer is able to charge higher fees than a data availability layer at the moment. And so
If I
this,
could, just a
yeah.
quick request, could you minimize the zoom controls under the more menu? We see them and they are covering the slides. I think you can click the
Okay.
more and hide the more with the 17.
Good. I mean,
Thank you so much.
okay. And so this means that we should aim to have as much of the valuable DeFi liquidity on L1 as possible. And like to finish off, like this is kind of like an illustration of this. Like I think like it's also a problem that like people see this often very in a very binary way. Like, oh, data has no mode. I don't think what anyone is saying. The question is like how strong is the mode? And I think the way we see it at the moment, at least, is that an L1 or like an execution layer with DeFi liquidity on it has a much stronger mode than like just providing a data availability layer. And so we should aim to keep that and to build that. And in order to have that, we need to scale the L1 sufficiently that DeFi can stay there. And yeah, that's it from me.
Great, thanks. Then you can end screen sharing. Oh, I can probably end screen sharing for you. Okay, perfect. Thanks. This was more basically meant as a bit of an intro talk, and then we go into the individual kind of technical presentations. So here, so I'll talk a little bit about this topic of scaling loops. And in particular, I really just want to focus on kind of like one picture here, and that is specifically Ethereum, the execution layer, has not had any ambitions around meaningfully scaling the throughput for a long time. So as this is now changing, we have to think about how do we deal with bottlenecks as they come up. And the way I basically I want to frame this is that there's really two parts to it. You have to identify the bottlenecks and you have to address them. Identifying is a pretty uniform process. Addressing them, we actually have several very distinct tools in our toolbox, and I wanted to take a moment to talk about all three of these that I call improve, contain, and change. And specifically, let's go through these individually. So first, on the identify side, people always talk about the gas limit and raising the gas limit. I think as we now start to get serious about doing that, we have to actually start being much more precise and high resolution about what that really entails. Because Ethereum throughput is not just one unified thing you can just scale up by a factor of 10, by a factor of 100 or something. It consists of all of these small individual bottlenecks that you have to basically, in a way, scale each one by one. And I just wanted to like sketch that out here. Like this is by no means meant as like a conclusive, comprehensive of the bottlenecks that we have. It's really more like to give you this idea, right? So basically, on the state, there's state size, just as how much over time have we accumulated, but then there's also the number of reads and then the number of writes in a block, and these basically do have subtly distinct bottlenecks that they touch. So state size is relevant for the disk space for nodes, but it also affects the read performance, right? Because usually databases degrade as this, or database performance degrades as the overall size of the data increases. It also impacts sync, and so on. So basically, like you can really look at this, and again, a more mature version of this is probably like 5 times as comprehensive. And the goal really has to be that you need to basically address identify and then address each of these bottlenecks individually. Although of course, often you can basically get features or other types of improvements that help with multiple of them. And just as a small example, as we got going recently with the scaling, impact the first bottleneck that actually was identified is this maybe counterintuitively this peer-to-peer DOS vector that directly is a function of the block size. So basically, nodes on the network, they just don't want to deal with too large messages that peers can send them, and so we really wanted to keep this like 10 megabyte limit in terms of like how large an individual message can be, and that's a bottleneck that wasn't all that obvious before people basically started looking into scaling. So basically, by actually getting serious about looking at the individual bottlenecks, gas limit no longer is the main thing that we really focus on. So then once we've identified all these individual bottlenecks, how can we handle them? Basically, once we know how close each of them is to becoming the main blocker for scaling. And here, the categorization that I would want to propose is improve, contain, and change. And what do I mean by those? So the first loop, and that's why I called it the kind of the scaling loops. The first loop here is, I would call that the engineering loop. So improve just means change the code, engineer a client that is more optimized around higher throughput levels to address the issue. So for example, on state databases, we've heard from clients that they were saying, well, the choice of database was informed by the rough size of today's Ethereum state. As we say, want to scale that by a factor of 10, they would have to look into choosing a different database, maybe even designing a new database type from scratch, these kind of things. So these are changes that require meaningful engineering attention, but they basically do not actually require changes to the protocol itself, right? So that's the first loop. And I would say that's the easiest to get off the ground. And that's the one where I think over the last few months, we've already seen the most initial progress. Because that loop can mostly happen within the individual client teams. Then we have the second loop, the contain loop. What do I mean by that? That's basically supposed to be kind of hot fixes for bottlenecks that we can't immediately remove with engineering improvements. And to look into that a little bit more, I kind of created this one slide. So what does it mean to actually contain a specific type of bottleneck? So as I said before, we currently one bottleneck that was identified is kind of the worst case block size. So what do you do here if you can't just immediately engineer your way out of that problem? So the first thing that you always have to do if you want to contain an individual bottleneck is you have to meter the bottleneck in protocol. There's no way around this. That's why I put it at the top. No matter how you want to then choose which option you want to choose in terms of containment, you always have to at least meter in protocol. What does that mean? You have to have a way doing block execution or something to basically have a agreed upon value of, okay, the total block size is this amount, or the total compute resources spent is this amount or something. You have to track that for that specific bottleneck in protocol. Otherwise, you can't have in protocol rules around that. So that's basically step one. And then once you have tracked that in protocol, metered that in protocol, you have three main choices of how you deal with such constraints. The first one is the simplest. That's a simple cap, and that's what we are looking into right now with the block size. The nice thing with a cap, you just say, okay, a block is invalid if it's larger than this amount. The nice thing it's really simple, and it is actually relatively it has this nice consequence that it does not impact the average throughput of that resource. So today's average blocks are already much lower than that 10 megabytes. And so even if we scale, we would never, with average case load, hit that throughput. The one downside is, and that's already, as I'm saying this, maybe obvious, this kind of capping solution becomes brittle as basically we have higher consumption, higher natural consumption than the cap would allow, right? So basically, if the demand for that resource goes significantly above the cap, the fee market starts to degrade, but also like block building, for example, becomes really difficult because you can't naturally order the transactions in an easy way anymore. So it's a very good kind of choice for a hotfix. It's not always the right choice for every kind of bottleneck. The second option you would have is to just make the specific thing more expensive. So you can basically, for example, we did this in the past where basically state rights became more expensive or things like that. It's also very simple, right? It's a simple change. You just basically make that price more expensive. It is also robust at high consumption because you just can't have more than that amount of consumption, so nothing degrades there. The one big downside there is that you actually decrease the throughput, the available consumption for that resource because it's now more expensive. And then the third choice, that's the researchers' favorite choice that core devs are always quite rolling their eyes at. That's basically the idea of multidimensional pricing. Often an overkill. It's definitely not simple. It can be the kind of the most principal choice because it is nice in the other two dimensions. So it actually increases the throughput of that resource because now you can consume that resource just in parallel to everything else. You no longer like have to choose, do I consume compute or data or whatnot? You can choose both of them. You can consume both of them. And it is also robust at high throughput. But again, not simple, so more of a choice if we can't do the other things. So that's kind of the contain loop. So that basically that allows us to contain things that can't immediately be improved. And then the third one is also obvious. That is actually make protocol changes, ship new features to overall alleviate the bottleneck and give us higher throughput. And of course, why would we not always just make changes? Well, I mean, first of all, there's not always changes that can increase the throughput of something. And the other way, but the other important point is also that these three loops operate at very different timelines. So the inner loop, the improve loop, can in principle happen very quickly. That's just like a rollout of a new a client release. Of course, still needs the work to actually get to that improvement, but once it's there, you can immediately ship it. Containments need hard forks, but you can add them relatively last minute to a hard fork. And then changes, new features actually require you to rework the execution layer, and that's of course by far the most disruptive, by far the slowest. So basically, you try to always stay at the basically quickest feedback loop and only move down as you need to. And then one last point there, maybe some people here on the call right now might be from the layer 2 side. It's actually interesting to see that the layer 2s have already been able to focus on the innermost loop, right? And so they've already increased client performance quite a bit, but and because they're trying to be VM equivalent, the outer loop is not available to them, and that's basically where we on the L1 can also help unlock things for them. And that's really the message I wanted to kind of have in this section of the call. Just maybe to explain why is the call is the rest of the calls ordered the way it is. I was trying to like roughly orient us to this kind of identify and then improve, contain, change ordering. So we'll have Marcin next talk about Perfnet a little bit, which is the main tool we now use to identify bottlenecks. And then we'll talk a little bit, Shaba will talk about an example of how engineering improvements can help. We'll talk a bit about containment in the pricing sections, and then the big section on changes to the protocol. So that's it from this. And so we can move on now to Marcin. I'm not sure, Marcin, do you have slides or screen sharing or anything, or do you just want to talk?
Yes, I would like to show my screen.
Okay, perfect. You can share your screen.
Do you see my screen?
Yes.
So I'm Marcin Sobczak from Nethermind. I would like to tell about Perfnet and other initiatives related to testing performance of Ethereum clients. Perfnet is a dedicated network designed to stress test client implementation by pushing parameters to the limit. We will run plenty of Perfnets, each targeting specific areas like block gas limits, slot timings, block target, and more. Our main goals are to define realistic, achievable, and secure limits for Ethereum's near future. We would like to determine how far parameters can be stretched while maintaining network stability. We want to understand what clients can truly handle and find areas where implementation can achieve significant gains from small improvements. We want to test various state sizes, including empty state, current mainnet, and significantly larger than mainnet, like 10x mainnet simulated state. First, Perfnet is already running. I pasted a link on the chat where you can find some insights. It has 4 gigagas gas limit for second slots. It was started with empty state. 5 execution and 5 consensus layer clients are included. We already have plenty of findings. Here are 2 examples from Nethermind. We also shared some findings with other client teams, but this one from Nethermind are fixed, and I feel comfortable with sharing it. I'm not sure about status of other issues, so it was just reported to client teams. You can have some insights on TerraGas WTF. It's actually like a brand new Nethermind UI, not released yet, but it will give you some insights into currently running Perfnet. We are planning to run a second Perfnet with parameters 60 million gas limit, 12 second slot, and started from mainnet state. And goal is to test parameters that are expected on mainnet in the near future. In parallel to Perfnets, we are doing worst case scenario research, analyzing the performance of isolated opcodes and precompiles. We want to identify potential bottlenecks and determine the client speed on which clients which clients can achieve without complex changes in Ethereum protocol. It's built on prior research. I think we don't have too much time, so I will skip the details. Like previous research led to finding numerous bugs in EL clients. We identified many performance bottlenecks, and we found important bottleneck in protocol, and it resulted with creating the AIP with MODEX gas cost increase, which will be included in Fusaka. All findings and conclusions can be found in the report. I pasted it on the chat. We found many vulnerabilities, pointed what need to be changed in protocol and what client-specific things must be changed at gas limit of 50 million. We pointed out what we need to change to be able to achieve 50 million gas. But in the previous research, we ignored state growth and focus only on EVM performance. Right now, we want to include analysis of state, and we plan to include additional previously untested opcodes and perform deeper analysis of already covered opcodes and precompile. We hope to find more sophisticated scenarios and hope to find new bottlenecks. First stage is to review and potentially fix all test cases which we already have and prepare more. And we are planning to run it on empty state, mainnet state, and artificially generated state similar to mainnet and significantly larger than mainnet, like the next. And at the end, you want to compare results across all these states and understand the impact of state size and history. Artificially generating state is like a task itself. There is already a great research done by Carlos Perez, and we are more than happy to cooperate in this area. So at the end, I would like to say that we are planning to run something similar to Hive test, which will be testing EL clients one by one and printing the worst performing test case, so opcodes or precompile. And we will run it this time on recommended hardware, like similar to recommended hardware for validators. Like in the previous scope, we were testing on a way slower machine. In the team, there will be QA engineers, DevOps, and core developer, and we will have the guidance and support on the entire Nethermind team. And that's all I wanted to share.
Perfect, thank you. And yeah, as I said, unfortunately, we don't have time for questions after every individual section. We'll have Q&A in the middle. Okay, perfect. Then we move on, and Shaba will talk a little bit about networking engineering improvement opportunities as an example of this first feedback loop. Shaba?
Hi, let me share the screen. And okay. Okay, so for those who don't know me, I'm Chaba from the Go Ethereum team. Recently joined. Previously, I was working on this research in Codex. As I didn't know your presentation, so I'm still on the identify side, but okay. So what I wanted to speak about networking, scaling reliable networking, finding some of the bottlenecks. So yeah, just a quick introduction to networking in a nutshell. I suppose everyone knows it. networking has discovery, dial, sync, mempool, all these kind of topics. Then we have CR networking, which has discovery, dial, sync, the block diffusion and attestation aggregations, and many other things. And between these two, we also have the engine API, which can be the bottleneck. So there are lots of things here, and any one of these could be the bottleneck, right? Plus, we have minimum node requirements, we have node heterogeneity, we have the number of nodes. So it's kind of a large space to map out. But let's see. Let's try to map it out. So is node discovery the bottleneck? We often hear discovery is too slow. Nodes are finding peers too slowly for this and that use case. We have solutions for this. I had a blog post on this called crawling it from this network fast, and it's crawling it in less than 50 seconds, finding all the nodes. So what you see there is that we can find 10,000 nodes in very low time. So discovery is definitely not the bottleneck. at the moment. Is dial the bottleneck? Dial is connecting to peers when we are connection-oriented, actually. And we have this problem in the EL, it's also there in the CL, that nodes are just simply full. They are just not accepting, even if we discover them, then we cannot connect to them. We have solutions to this. It's more around having separate inbound, outbound peer pools. And then we are doing peer dropping, we are scoring peers, we can have protected peer pools. What you see there is kind of the current state, well, a state a few weeks back in Guess how fast you can connect peers and how we changed it now. So now you can, actually it's not yet merged, but soon you will be able to ramp up your peer count much faster than before. Yeah, so dial is a bottleneck, but we have solutions there. Sync. Sync is also a bottleneck, and the other thing to realize is that we have two use cases, and we typically focus on the first one, which is a node which is trying to sync, and then we are thinking of sync speed and so on and so forth, but that's not the real bottleneck. The bottleneck, if there is one, is the second one, which is, I call it system sync. So if we have kind of a catastrophic event and basically all the nodes have to sync, like a large portion of the network has to sync from a few nodes. So if sync is the bottleneck, then that's the use case we should look at. And well, we don't have a solution. I'm working on something which I'm calling smaller sync. So this is basically making sure that syncing nodes are optimally using each other's resources in a real peer-to-peer fashion. It's kind of there to some extent, but it's not facilitated by the current network. We have elements of it, and we are working on this one. So I hope sync will not be the bottleneck, but I can imagine it is now. CR block diffusion. Is it the bottleneck? I don't want to waste too much time on this. In 2023, we were measuring block diffusion times, and we found that 2 megabyte blocks are still diffusing okay-ish, but it was not okay. Smaller ones were diffusing. Since we had quite some research on this, that we have segmentation, we have erasure coding over the segmentation, we have diffusion over different topics, we have batch publishing, we have push-pull phase transition, we have LLC. So we have a bunch of techniques there in research, which might speed this up. Attestations. Attestations can also be the bottleneck, right? Again, we measured it in 2023, and basically what we have seen that attestations are propagating really fast in the network. So I wouldn't expect this to be the bottleneck. Maybe time to revisit these measurements, but it was really fast. As you can see on the right side, in 1 second, that's in milliseconds. So in 1000 milliseconds, everything, no, actually, oh, yeah. It was slow. Well, then I put it there actually, because that's 10^4. So attestations might be the bottleneck. Actually, I don't think so. But this is to revisit defensively because I just looked at this chart wrong, and there's this plus one more zero there. Mempool. So this is a recent measurement I did. Whether we have bottlenecks in the mempool. And what you see here is the speed of diffusion of individual transactions in the mempool. So this is what you see there is time before the block arrives to us. And then when the execution node actually seen the transaction first time. So there you see one specific transaction, which we have seen first 12.5 seconds before it was included in a block, before the block arrived, which actually included it in the mempool. And then you see how many information we got from it from other ER nodes. And you see that 2 seconds later, basically 85% of the network had that transaction. So information is spreading very fast in the mempool. Here you see individual transactions, and then we can change a little bit the view. This is where we have a common start line. So when we first hear about the transaction in the EL, we start to map out who we hear from, and then we estimate how much it might be diffused in the mempool. And we see that this is transactions are spreading really fast. Even block transactions are spreading fast. big transactions, blob transactions. We are not speaking of blobs, but we can speak of big transactions because from this point of view, it's the same. 6 blob transactions have 700 kilobytes, and in 2.5 seconds, it's kind of spread in the network. So is this a bottleneck? Well, not yet. When we're scaling, it might become, but we have some measurements on how fast it is. And kind of that's it from me. The next one will be on finding and solving bottlenecks, but I don't know when. So this is where
I also didn't want to put you on the spot with that. I think I was just like trying to roughly, order them in a way that makes sense for people to follow along. But I think yours was actually perfect in between identify and engineer and solve. So that was great. Thank you. Then we'll move on to the 2 talks around pricing. First, Davide will briefly kick us off with a few general words, and then we have Jacek, who will talk about the repricing EIP. Shaba, can you end the sharing? Perfect. David, are you here?
Yep. Let me present.
We can see your screen. You can go ahead.
Yeah, so I wanted to introduce the work we're doing on pricing. We have this EVM resource pricing working group, which has been going on since January, mainly led by myself and Ansgar. We've been focusing on kind of 2 areas. The first one is like short-term pricing improvements. As example, like we discussed, like we had Marek from Nethermind present like their report, and which then became like the MODEX gas cost increase. We also had a few sessions discussing like repricing efforts, and this is then became the EIP that Jacek will present right after myself. And we have a few recent ideas, for example, adding a standard config for gas costs, like especially since we are and will be starting to do like more performance testing. We feel that potentially having this standard config across multiple clients with all the gas cost parameters could really help with that, and also with making changes like easier in the future. And we have other discussions around like memory cost pricing, etc., just to give you an idea. And then the second aspect is, I guess, less on the containment side and more on kind of the improvement side, like the next session, which is on like medium-term changes, right? So here is about new mechanism and like research to support them. Yeah, one example is this EIP that was already out before from Vitalik and Tony about increasing cold data cost. That's like introducing like some change on how we compute like the cost of different resources in the mechanism itself, not just in the parameter. And then we had some research on multidimensional gas metering from Maria Silva. Like, yeah, this started in the call. Maria then got a small grant, and she will be joining RIG soon as a new member. And this also informed like some recent work from Thomas on proving costs. Yeah, so then another area that we're actively exploring is around like VM execution versus proving costs, like both like in general, but also related to like how we could change pricing constants, or how we would need to change pricing constants to adapt to the switch, like from like execution centric to prover centric. Yeah, so this is just a summary. If you are interested, I will drop the link to the working group in the chat. Right now is mainly like the core devs plus like other people in the ecosystem interested in resource pricing. And yeah, I think this was just like introduction from me. I'll leave the floor to Jacek to discuss his EIP.
Okay, thanks. Let me share the screen. Great. So hi, my name is Jacek, and let me just present you the EIP that we've been working on, which is general gas repricing. So come on here. Basically, what we propose is a reduce of gas cost for most of the opcodes, simple opcodes from whatever they have now to one. There are a few exceptions, but you see the general pattern. We just want to reduce the cost of it. In most cases, this is not drastic reduction of cost, but if you, for example, see jump I, this is seems like a drastic. I'm explain it later why it is so, but let's look at the proposal further on. We also propose to change the warm data access cost and TLOD T-store from current 100 to 5. This is because warm data access might be looked at as a kind of a cache, and we proved that EVM clients are actually very good at handling it, and it doesn't cost that much. Further on, we looked at the memory cost, and memory cost is usually made of two components, the quadratical cost and per word. What we propose is to remove this per word element and leave only quadratic cost for safety purposes. Let's call it that way. Now, we come to question, why? So these numbers that I showed were not made up. We ran some research. We took 7 popular Ethereum clients, created 50,000 programs, bytecodes, and we ran them really for thousands of hours, literally. And why did we need so many benchmarks? To produce charts like this. So what we see here, for example, is a diff opcode to run in Aragon in this case. And we can measure how size of arguments affects the execution time. And we can see the bigger first argument, the longer it takes, and so on, but not that much. So by getting all of the opcodes and precompiles together, looking at some most expensive edge cases and so on, we can create charts like this, which compile the execution of opcodes for different clients, compare them to the current gas cost schedule. And by running some analysis on the data, we came up with the numbers that I showed you earlier. Now, if we are to implement this EIP, the first obvious impact would be a cheaper transaction cost. As we can see here from some examples that we ran, for a typical most popular transactions, the reduction is not that big. There are some edge cases, like for example, op breach, which will be reduced, the cost will be reduced significantly. Not because we like OP labs so much, it's because the actual computational cost behind the OP breach is much lower than we charge them at the moment. Looking more at the impacts of implementing such an EIP, first, by doing it, we make sure that the cost reflects the true computational complexity and therefore cost of running those computations on nodes. And we restore a balance between opcodes. As I showed you before, we can prove that jump operation is not much more computationally complicated than push zero, for example. And it should be priced at the same level. There are some of the side effects, let's call it. So we keep the storage in that schema, we keep the storage price at the same level while lowering cost of computations. That might promote in the future new contracts that are heavier on computation in order to save some state. We also run the next side effect would be running the quite significant gas change, but opens a door for the future gas changes, presumably for every hard fork. And then, this is purely my speculation, but we can assume that by introducing such EIP, clients would need to have some configurable gas cost schema, which might find some other usages that we don't foresee now, but it might be useful for the future. Yeah, that somehow concludes the EIP. Of course, there are lots of details, lots of data. If you want to look at the link some more here, yeah, the project was called Gas Cost Estimator. Yeah, that's it. Thanks.
Perfect. Thank you very much. Those were all great presentations so far. As expected, we are a little bit over time so far, but behind time. But the nice thing is at least now this was the most subdivided part of the call. So from now on, we'll have fewer and longer slots. We still have 5 minutes for Q&A. So if there's any specific questions for any of the speakers so far, anything you'd want to briefly bring up or any comments, now would be the time. Otherwise, we can also immediately jump into the next part, all the better, then our call will not run over so much. Okay, then let's actually start the next part on time. So then Francesco will now talk about one of the new features that are being heavily discussed right now, which is delayed execution. Francesco, do you want to get going?
Hi, yeah. Can you see my screen?
Yes, let's see if that works. Yes, I can see.
Okay, yeah. So this is, I should say, also like this is joint work with Tony, but also like the slides very much were made by Tony originally and just modified by me. But I'll be presenting it. So yeah, I'll be talking about delayed execution. Probably most of you have heard something about it, but still like a recap, kind of what is the point of it, and then mostly dive into specific issues and how we solve them and kind of the approaches that we take. So yeah, the starting point is block validation today. It looks more or less like this. At time 0, there's a block proposal, ideally. Time 4, there's a attestation, and then for like the first time where the 4 choices run after a testing would be the next proposer. And in practice, like today, so the time that's kind of useful today would be the time between T0 and T4, so 4 seconds. In practice, it's not all kind of filled time. We have some part of it that's used for propagation, not very much, not the whole slot, and then like a tiny portion that's used for execution. I think on average is around 100 milliseconds, but it can be, there's some like variance there, and there's worst cases that are much more than that. But yeah, more or less, your average slot might look something like this. So ideally, we maybe don't want to only take like a tiny portion of the slot for both of these things. And like specifically for execution, I mentioned 100 milliseconds. This is less than 100th of the whole slot time. So ideally, we really would like average execution to be a bit longer than that. And yeah, the idea of delayed execution is basically to kind of safely allow time for this. And so to actually allow execution to happen after this T4 kind of attestation deadline, or I mean, the attestation deadline in general, like we could also think of moving this further up the attestation deadline, just structure the slot differently. But either way, basically, the idea is to not constrain execution by needing to be over at the attestation deadline, so that we can potentially dedicate more of the time before testing only to propagation, and then time afterwards to execution. Then how exactly, how long should this bar be? It's not, you could say, oh, this could go all the way until the T12 time. It's just whenever the next proposer needs to basically have managed computing the state in practice to like basically have executed know the state and be able to start building. Probably that's not really realistic. You want like building to start a bit before. You probably want to not take the whole time because of syncing concerns. So there's other considerations, but the general idea is just we want to allow for more time. And then, yeah, another consideration here is if we think further to zkAVM world, this time can also be used for proving. So yeah, I think this has been talked about a lot, basically with daily execution being a bit of a prerequisite for having zkAVM 101, whether directly or through native rollups or essentially in whichever form. And then, yeah, the question would be, okay, how can we actually attest without executing the block? Like that seems somewhat unsafe. In particular, like we want to validate the block that requires executing. What do we do about that? And there's essentially two like families of approaches. One is what I've been calling optimistic attesting, which is basically just saying ignore the problem completely, like just pretend it's not a problem. Don't actually do any validation when before testing. You could even extend this to beacon blocks. Just don't check anything. And yeah, if then it turns out that something was invalid, you kind of deal with the consequences in the fourth choice. So you could basically just throw out the block, mark it as invalid. And I mean, it's not as simple as that. There's other things you need to do. But yeah, essentially, it's an approach that's very much just trying not to deal too much with the problem. And then the other approach would be static validation. So somehow we want to like massage the validity rules in a way that lets us essentially be sure that the block is valid without doing any execution. So like statically being able to validate the block. And yeah, you could think of these as like one is a CL approach and brings CL complexity, in particular, mostly for choice complexity. And the other one is mostly of an EL approach that kind of tweaks a little bit the execution and validation rules for the EL payload. And we'll mostly focus on the second one today, at least. So yeah, the starting point when thinking about static validation is the block today, in particular the block header, and the part that's relevant to us is the execution outputs. So these are like the fields in the header that are things that you only basically can know after doing execution, like can only validate after doing execution. So the state root, the like logs bloom, request hash as of the last fork, receipts, transaction root is not exactly right. Like you could actually compute this before execution, but it somehow still fits here based on what we discussed later. Or anyway, just don't worry about it too much. And then gas used, like you cannot know how much gas was used in the block if you don't actually do the execution. And the idea is, of course, that if we want to do static validation, the block should not actually be committing to these execution outputs. Like you can only actually check these, know that they're correct, if you actually do the execution. And so you cannot know this in advance just by looking at the transactions, essentially. And so the first ingredient for introducing static validation would be to defer the execution outputs. So basically take the header just as it was before, but now all of those fields, they essentially would refer to the parent. So instead of having state root, we would have pre-state root. I decided to call this one, or I guess we've decided in the EIP as well to call this one pre-state root, because that's generally what people have been calling it. Everything else is called parent something, which maybe it's a bit confusing, but it's all kind of the same. They're all like fields that refer to the parent. Essentially, they're like the post or like the execution outputs of the parent. So yeah, like parent receipt root would be the root that you get once you get the receipts from the parent. And yeah, same for everything else. And so in the next block, you could actually then validate the execution outputs of the parent, but in the current block, you just don't have those at all. Or you don't have the ones for your own block, essentially. And yeah, so once you've done this, one question is, what can still go wrong? How can a block actually turn out to be invalid? And essentially, I mean, there's different ways that this could happen, but you can basically boil it down. Once you look at the things that are actually challenging to deal with, you can boil it down to basically two things. At execution time, it could be that a transaction is invalid because either the sender is not sufficiently funded or the execution exceeds the block gas limit. So yeah, the first case, it could happen in different ways, but the primary way that's sort of problematic is like an account could be drained. So it could look like the sender is funded at the beginning, but then it turns out that it's not, and this is possible as of 7702. But either way, this is a problem that you still need to somehow deal with. And then yeah, just execution could exceed the block gas limit. Like if you don't execute, you don't actually know that you don't know what the gas use is. You don't know that you're actually staying within the constraints. And so what we could do to react to this problem is we could just skip the invalid transaction. So all of these problems, somehow they're related to like a certain transaction being invalid. Either, again, just the sender cannot pay, or it would go over the gas limit, or it could go over the gas limit. And so we could just somehow skip these transactions and only leave the ones that are fine. And the issue is, even if we do skip them, they're still committed to, they're still part of the block. This like, block hashes still exist in the chain. People will still keep this block in the history. And there's all this data that is skip transactions that are not actually paying a fee, but they're still part of the history and everyone has. And this is essentially the free DA problem. Like you could, in principle, use this in a kind of a bit contrived way to construct like a weird DA layer that's very cheap. And there's essentially three techniques that we have, or at least these are the ones that we've encountered to do something about free DA. One is that you could pre-charge either the Coinbase or the proposer, basically someone that is like in charge of the block, for the inclusion cost of transactions. So like the problem is that these transactions are not paying in case they're invalid, but you could charge the person that's somehow responsible for them being invalid. Like if you don't, you charge the Coinbase and a transaction turns out to be invalid, it's their fault. You just don't refund them, and there's no free DA in that case. So that's one approach. That's actually the one that we sort of started with. And then you could pre-charge the transaction senders instead of the Coinbase. So you could basically do the charging of gas fees and transaction value before the block instead of before each transaction, which is what happens today. And then another thing you could do is you could revert the whole payload if there's some invalidity that happens in it. So basically, you just pretend that the payload had no transactions at all as soon as anything is invalid. This doesn't quite prevent free DA because, again, the data is still there, like the fundamental problem is still there. It essentially is just a way to make it costly, but without actually kind of really specifically charging the exact cost. Like in one, the approach one, we really charge the exact cost for the inclusion of transactions. So like call data, blob fees, and like all these kind of things. But in three, we don't. We kind of just charge this cost of which is basically the opportunity cost of missing the whole payload if you really want to use it as a vehicle for invalid transactions. And yeah, something that so these are some approaches. One aspect that's not obvious that kind of helps us in choosing which or like that a bit restricts what we can do is actually the interaction with Fossil, something that looks completely different, but turns out to be quite related. So if we do on Fossil, it does impose like a big constraint in how we can think about delayed execution, because it adds this post-execution condition that you need to kind of check before attesting to an EL payload. So basically what you would be doing is when you attest, you also do some IL inclusion check. Like basically you have some inclusion list, and then you essentially want to check that if the block actually satisfied the inclusion list, is what we usually say. And what this boils down to is you basically take some transactions and then check kind of against the payload if they could be appended at the end of it. And if they could have but didn't, then you don't want to test the block because it's sort of failed in this inclusion check. So there's essentially this like append validity check, where you want to check like the possibility of validly appending something to a block. And yeah, this is, if you think of how execution works today, this is something that you cannot actually do statically. Like you cannot just statically determine if a transaction can be appended to the block, because again, the sender could be drained, the block could be full. You just don't know these things in advance. And yeah, so this like static append validity check kind of complicates things. Again, as I already mentioned, like EIP 7702 kind of contributes to this. Like you could have UAs that are drained during execution, and there's no way to statically detect this. Yeah, so basically in isolation, if you try to just use approach 1 and 3, which were the pre-charge Coinbase and the reverting the whole payload, and actually even optimistic testing, it would fail at giving us like a way to do this fossil check. So by themselves, these approaches are all not compatible with fossil. And so if we do want compatibility, this kind of already tells us that we should look in the other approach, which was this one, pre-charging transaction senders. And yeah, what this looks like more or less is this. So today during block execution, you do this charging of transaction value and max gas fees in advance, like of each transaction. So you like go through all transactions and you charge the sender the max possible, and then you do a EVM execution. And what's missing there is you would also do some refund at the end. And then in kind of this world where we're doing pre-charging to enable delayed execution, there will be some kind of static validation at the very beginning before doing any execution, and this by itself should already tell us that the block is fully valid. Then we would charge all of the senders. So this would be sort of the beginning of the actual execution of the block, where we actually start making state changes. And then we actually go to the transaction execution. But here we don't charge senders anymore. Like all of these transaction values and max gas fees have already been basically dealt with and like reserved essentially in advance. But we would still do the refunds just the same. So like from a user perspective, there will actually be no difference. It's more of like how the accounting is done in some sense. There is like a little quirk that it breaks the use case of funding an account during the block execution. So all the accounts would have to be funded at the beginning of the block's execution. They couldn't be funded somewhere in the middle. But this, as far as we can tell, is the only thing that would break for the users essentially. But yeah, still this is not enough. You could still have some like essentially you could still have invalidity that gets introduced by exceeding the gas limit. So pre-charging senders only prevents the first problem where a transaction is not funded, but it doesn't prevent the problem where we just exceed the gas limit during execution. So that's still something that we need to deal with, that by itself, this pre-charging senders just doesn't do anything for, whereas the other approaches could. And then the other thing is it actually also doesn't quite work with for fossil, because this append check requires knowing how much gas is available. So if you basically want to check that you can append a transaction at the end of the block, you would want to know how much gas can this transaction actually fit in the gas that remains. And you couldn't know this just with this approach essentially, because again, this is something you can only know after executing. And yeah, so before, if you remember, we had gas used also kind of turned into parent gas used as a field that's an execution output. So it's something that it's supposed to be deferred in these delayed execution approaches. Because again, we don't want to commit to something that we cannot verify without doing execution. But actually, if we could have gas used in the header and we could trust that it's correct, then that would solve all of our problems. It would enable us to, going back to here, it would enable us to know that execution doesn't exceed the gas limit, and it would enable us to know how much gas is available, and thus fully completing this append check. But we can't really have this in we can't really trustlessly have this without doing execution. We can't verify this. But we could basically combine some of the approaches that we have, actually have this gas used, but not do something if it's incorrect, essentially. So we could start with this approach 2, pre-charging senders, but then if the gas, and have the builder declare this gas used in the header. But if it turns out that it's incorrect, we could revert and basically make the whole payload a no-op. So this was like approach 3, but specifically only if the gas used is incorrect, because this is the only way that the payload could turn out to be invalid in this kind of approach. And so, yeah, what things look like at the end, once we combine these two, is that the builder declares the gas used in the header. If it's wrong, we revert the whole payload. We do all of these like same things that I mentioned before about pre-charging senders. So we charge all of the transaction value and max gas fees before the whole block execution. And at that point, we already know that the block is valid. It might turn out that the payload reverts, but we still consider the block valid. And we can do this fossil check. So you can essentially statically determine fossil satisfaction by doing this simple check. You check that transaction gas for one of these inclusion list transactions is less than the gas available, so it fits in whatever remains. And again, you can do this by looking at gas used and kind of trusting that it's correct, because if not, the payload will be anyway empty. And then, yeah, you just have to check also, could the sender have been charged or pre-charged the transaction value plus max gas fee. So essentially, was the sender sufficiently funded at the beginning of the block? If all of these conditions check out, then you know that the transaction could have been appended, and you can do your basically fossil check based on this. So you decide if the builder actually complied with your inclusion list view or not. And yeah, that's basically it. I mean, there's more to say. There's I mean, you can already see from this, there's these two approaches being combined. I didn't read what's here, but yeah, you could combine other approaches I mean, the same approach with the Coinbase charging or with optimistic testing. There's a bunch of other ways that you could do things. And in this ETH research post by Tony, we kind of go over a lot of the possibilities and their combinations and discuss like what are the basically, yeah, where things go wrong and like what characteristics the different solutions have. And then, yeah, just quickly, here's also a link to the execution specs for this specific last approach that I mentioned, which I mostly focus on because it's the one that we feel more strongly about at the moment. And also the EIP, which again is right now changed to this last approach. Yep, that's it.
Perfect.
Thank you.
Thank you. Yeah, and again, just for context, right? Like basically the idea for the call was to have the first section be a bit more like a rapid fire of all these individual topics to give an overview, and then have the second half of the call to basically dive into the specific two main focus areas of the EL research over the last few months, which has been delayed execution and block level access lists. So we have a call from Tony coming up in a second on block level access list. But before that, we wanted to also briefly have Potus talk about ePBS again. ePBS is, of course, already further in a different stage, no longer so much focused on research, more on the kind of prototyping side of things. It also basically it's relevant here to contrast with delayed execution, because it also reorders what we do in the slot and when. Point being that for now we just wanted to basically present both of them. The research hasn't really progressed much on basically how these two could be combined, or basically what the relative trade-offs are. So it's not about comparing them. It's really just about reminding us that ePBS is also like a very relevant second feature in that design space. Potus, do you want to take it from here?
Sure. Let me just share. I don't know if you guys are seeing this. You can?
Yeah.
Okay, good. So this is going to be very fast. I was told to like point what are the scaling features of ePBS. And so it's going to take just 1 minute, just 2 slides. First of all, What ePBS does, it removes the payload and the block broadcast from the hot path. It's exactly what Francesco was proposing. There was this moving execution to after attesting. Well, we not only would do that, but we also would just remove the broadcast altogether. So today, instead of like having 2 seconds from broadcasting the whole thing, payload, blobs, and blocks, make it available, and then executing, and then attesting, you now will just only need to broadcast the consensus block. Then later on, after the attestation deadline, the broadcast of the payload and the blobs would come in. That's it. That's all of the scaling properties of ePBS. So that's essentially my whole presentation. We move to this setup in which the broadcast happens in 2 stages. First the consensus block, then the payload and the blobs. Well, so now what is the trade-off with delayed execution? This achieves delayed execution, and this achieves also delayed broadcasting, which is the biggest bottleneck, which is bandwidth. So that's it. That's for scaling. I'll mention a few things about the trade-offs. So the main problem in trying to, and the reason why it's much simpler to implement in some sense than delayed execution is because we don't need to deal with things that might be committed to the state that end up being invalid. We don't need to pre-charge anything. We don't need to like deal with like refunding if there's any refund or anything like this at the cost that if the payload appears and is invalid, then we need to deal with, instead of blocks being there or not being there as today in Fortress, we need to deal with the consensus block being there with the payload, the consensus block being there without the payload, that's the new entity, the empty slot, and neither the consensus nor the payload are there. So for choice, it's becomes slightly more complicated because it needs to deal with the situation where the consensus block might be there, but the payload is not. And that change is essentially the unique change to for choice in the consensus side. So what is the status of this? Well, as I mentioned, we don't need to deal with payments or anything. This is absolutely trivially composable with Fossil. The builder would just like send in the bid a list of inclusion list that it satisfies in the payload. We just commit to that list on the consensus block. And later on, if the payload doesn't satisfy the inclusion list, we don't need to care about the fact that we committed anything on the consensus side because we just ditch the payload as invalid because it didn't satisfy the inclusion list. That's it. No dealing with anything on the execution side. In fact, ePBS is the minimal approach to separating the consensus block from the payload. It is a step forward. I assume that is necessary because at least myself, I cannot think of any way of implementing any of the things that are in the roadmap, like APS, execution tickets, or none of those things that rely on a decentralized attester set and a centralized builder set, not using a mechanism that separates the payload from the block. It only involves changes in the consensus side, doesn't touch at all the execution engine, it doesn't touch at all the execution layer. You might want to make some changes in the execution engine to help in some things, but as it stands, ePBS doesn't involve anything from the execution side. That means that it can be tested alone in isolation without any other components, and it's already implemented in 2 clients, in Prism and in Teco. That's it.
Perfect. Thank you. Yeah, and again, the reason for why I asked put us to keep this presentation shorter is just that ePBS has been around already for longer, so there's less kind of new news on how it works and everything. We went through this in the past. I just wanted to make sure people have top of mind that there are now 2 proposals that both deal with kind of reordering the slots, and I think over the next 2 months or so, the focus will be on working out how do they relate to each other. What are trade-offs? How can they maybe be combined? These kind of topics. But that's out of scope for today's call. It's really more about pointing out that they both exist. Okay, then we move on to the second main topic for the kind of the feature part of the call, which is block level access lists. Tony, do you want to take us through your slides? We
Oh,
can't hear you yet.
I couldn't find the unmute button. Already shared. Okay, perfect.
We can see your screen.
Wonderful. Let me start a slideshow here. Great. Yeah, hello everyone. My name is Tony. I'm a researcher with the Ethereum Foundation, and this talk or this presentation will be about block level access lists, EIP 7928, which is a very recent EIP, but it has, in my opinion, great potential to allow us to significantly scale the L1. So before we get into block level access lists, let's look how the situation looks today. This is a very simplified picture here. So today, for every transaction that we have, for every access, for every call, we basically have first some I/O going on, some discretes, for example, and then the actual EVM execution. Of course, this is very much simplified, right? Because in practice, clients handle that very differently. They load state just in time. They have prefetches running that already kind of figure out which storage or which state is accessed. But just to set the scene, this is basically how it looks today. And over the duration of a block, we get a picture like the following, where for every transaction, we execute them in sequence because transactions are oftentimes dependent on each other. So transaction 2 relies on some storage slot that transaction 1 wrote to. So we cannot really execute transaction 2 at the same time with transaction 1 just because of dependencies. And putting that into a Gantt chart like I did here, you can see that this sequence costs us some time in the end because we cannot really parallelize transactions. So we need to kind of execute them sequentially, being not very efficient. And where we would want to be at is a situation like the following, where assuming we have an infinite number of cores or as many cores as transactions in a block, of course, that's unrealistic, but just as an assumption here, then we would basically get a transaction execution time or a block execution time of the execution time of the heaviest transaction. So we would parallelize transactions and then execute them in parallel. Even better, what we could do is parallelizing I/O and EVM execution. So what we get here is an even more efficient outcome because we can start executing transactions before we have even loaded stuff from disk. And in the end, after doing the state lookup async, we just compare values and check if everything is valid. And this brings me to the topic, to block level access lists, because this is exactly what block level access lists are trying to tackle. So what are block level access lists? Looking at the block, how it looks like today, we have our block coming with a header, with transactions, withdrawals, and simply speaking, we would just add a new field there, which is called the block access list, which can be thought of as a kind of a cheat sheet for validators to validate faster. So we take builders and we enforce them to make the life of validators a little bit easier. And for that, we use exactly those block level access lists that validators get for blocks, look at them, figure out what the best parallelization strategy is, and then execute them. And the simple one-liner here would be that builders provide mandatory access lists that let validators verify blocks faster. Right, so now that we kind of have some clearance on the goal and what we're trying to achieve, let's look into the design space. So first of all, we can differentiate here between what do we want to put into that access list, right? First of all, the most straightforward thing would be to put storage locations into it, storage locations, addresses, and keys, basically. Second, we have storage values. So we go one step further and we not only indicate where state is going to be touched, but also which value is going to be touched, read or written to. And finally, state diffs, because at the point when we already provide values, it might make sense to directly go all in and provide the full state diff.
So first of all, when it comes to the storage location, as already said, this is kind of easy and straightforward. We have an address and a storage key. And having those storage locations is already quite nice, because what you can do is you can already parallelize I/O. If you know what is going to be needed, you can load that in parallel. And then you get already some very good parallelization for average blocks. Because usually transactions in blocks are not that dependent on each other. Only a small fraction of the transactions are really heavily dependent on each other, but most of them are not. So for the average case, you get some quite nice parallelization just by having the storage slots, because you already know which transactions to distribute to which core, such that they don't interfere with each other. Of course, you don't get any parallelization for worst cases, and this is kind of the problem we have to tackle here. Right, let's move on to storage values. Here we can differentiate between what type of value do we want. We can distinguish between the pre and the post block value and the pre and the post transaction value, where the pre block value is just the value of a certain storage slot before executing the block, and the post value is after executing the whole block. And more interestingly, on the right-hand side, the pre and the post transaction values, those are, I would say, more interesting, more useful. And because, for example, the pre-transaction value of a storage slot would give you the value right before executing a certain transaction. So not the value before we executed the whole block, but right before executing a respective transaction. And the post-transaction value is just vice versa, the value after the transaction. And finally, the last item I had on my design space slide was the state diff. And the state diff is kind of simple and very small, because we don't need much to be put in there, because most of the state can be derived from just looking at the block, just looking at the transactions. But for nonces, for example, if there is a create or create2 deployer, we don't really know that by just looking at the block. And for balances, we also don't know if there were balances trained through some sophisticated operations. So we would need to have a balance delta of all accounts that had ETH balances changing in that block access list too. So this brings me to the last part, kind of what is the best design here. And before we get into the best design, let me give you some quick facts about execution and about ongoing research there. So it turns out that when we look at the time we spend on transactions, it looks like execution is not the bottleneck, and it's not I/O. Big shout out to Gary here at this point, because Gary from Geth provided me all those figures. So for Geth, at least 50% of the time on average is spent on the EVM execution and only 13% on I/O. Second, prefetchers and other methods that make transaction execution more efficient, they already do an amazing job, especially for the average block that we see in the network. But we cannot really scale, because those prefetchers are very performing bad when it comes to worst case blocks. And finally, 60 to 80% of transactions are independent. So here you can just distribute them across your cores without thinking much about parallelization. Right, so let's look into the design trade-off. And those two designs are the most promising one, as it turned out during month-long discussions by now. And they come with, so those two designs have the storage location specified. So we have a block access list that specifies the storage location, so the address and the storage key. And one of them specifies also the post-transaction values of storage slots that were written to, and the other one provides all pre-transaction values, no matter if it's a read or a write. And as you can see, initially it looks like, of course, when we only compare the execution time, the kind of design on the right-hand side is better off, just because it's even faster. We get an execution time that is the maximum of parallel I/O and parallel execution. But the problem here is, as soon as we add worst case sizes, we see that the other design that doesn't get you parallelization between EVM execution and I/O, but it gets you this sequence of doing I/O and then the full parallel execution. And here we get way smaller worst case sizes. And importantly, the 0.9 megabyte, that's below the call data limit, right? And this is, in my opinion, something we should really be careful about. So the left-hand side, we are below the call data limit. On the right-hand side, we're above the call data limit. So if we would introduce something like block level access lists with storage locations and the pre-transaction values, then we would actually create, we would get to a new worst case block size of 1.51 megabyte, which is one block doing a lot of S loads, thereby being allowed to specify a lot of values in the block level access list. So comparing worst cases, I would say the left-hand design is definitely better. Finally, I put that into this table here too. And because I haven't really had time to cover it, but on the very right-hand side, you can see the column with state diff. And the cool thing here is if we have block level access lists with storage locations and the post-transaction values, then there is not that much left to get to a full state diff, right? The only thing that is left is the nonces and the balances, and then we would have a full state diff. And it turns out that this might be helpful for syncing, especially for the healing phase in SnapSync. So blocks, validators would get blocks that includes the whole state diff, which is of course nice if you only want to maintain certain parts of the block and stuff. You don't need to execute anything. You can maintain the state without any guarantees that it's correct, of course, but you can maintain the state without execution. Right, and this brings me to the end of the post. I put some QR codes here with some further readings, ETH research post that I posted today, the EIP itself, and my latest website, dependency.pix, where you can look into transaction and execution dependencies of Ethereum as of today. Perfect, thank you very much.
Thank you, Tony. Yeah, perfect. Then basically we are at the end of the main kind of section of the call. We can very briefly hold again, see if there's any questions or any comments up to this point. Otherwise, then I would hand it off to Vitalik to talk about the longer term view here. Maybe that's best. And then we have this section. So basically the idea is we're now at the end of the main 90-minute window. So if you have to hop off, that's fine. We'll now move on from this kind of short-term focus. We talk about more the bigger picture questions. And then we'll have open discussion sections for the people that are still on the call at the end that Micah will kick us off for. So Vitalik, do you want to? Oh, sorry.
Yes, great. I'm here.
Lucas, do you want to say something now? Otherwise, we can also
one thing to point out that this block level access list is very similar to vertical witness, but gives us actually less than vertical witness as far as I understand both. So maybe just switching to vertical and using vertical witnesses might be another alternative to do that.
Yeah, and
I think my own understanding here is that like the maximum version of an access list actually gets us like basically the same information, right? And this is actually a great segue, right? Because I think it's like the point, like I'm here to talk about some of the longer term, right? And the way that I think about it is that basically the next 4 years of Ethereum are going to involve a lot of repeating a similar design pattern, where that design pattern is basically one actor does some extra computation in order to add some extra helper information. And then that helper information makes life much easier for everyone else, right? And to me, block level access lists are the first step in doing that, right? And block level access lists, so like they give you enough information so that you can parallelize verification. Then the next step after that is that you basically take the block level access list and then you add on top stateless witnesses. And if you add stateless witnesses on top, then that lets you verify blocks without having any of the state yourself. And then the third step in that same trajectory is the full zkVM, and the full zkVM basically means like one person proves a block, and then everyone else theoretically doesn't actually need to do any computation at all, right? And I think like we could definitely have some debate on the timing of some of them. Like I know there's some people who are bullish on zkVMs happening quickly. There's people bullish on statelessness happening quickly and so on. I mean, like my personal view is that statelessness coming very significantly before zkVM makes sense, just because like ZK Stark technology still relatively has a somewhat higher level of risk, especially for us to get comfortable with layer one, depending on it. But I think like regardless of the details of this, right, there's this like big picture pattern going on, which is that we're going from every node in the network doing the same computation to basically verify by repeating the thing the first guy did, to a model where the first guy does some extra work, and in exchange, everyone else's verification job gets much easier. And the underlying idea behind all of this, right, is that we're trying to scale Ethereum, and we're trying to make Ethereum and Ethereum's guarantees accessible to more people, right? So we're trying to make self-sovereignty, censorship resistance, verifiability, open source, open state, open execution, all of these things accessible to a larger number of people, basically because if we don't, then that activity will happen on platforms where users are going to get a much smaller set of those guarantees. But if we do that naively, then it becomes unviable to run a node, right? And we, of course, really don't want it to become unviable to run a node. And so what these technologies do is they basically say, well, instead of having one type of node, like the network is becoming somewhat more heterogeneous, and effectively, with a smaller number of helper nodes, you're able to massively decrease load for a much larger number of nodes, while at the same time throughput keeps going up, right? And this is like a very delicate process, and I think it's a process that we really do need to handle responsibly, and really make sure that we understand what we're doing, that we understand what we're gaining, we understand what we're losing, and also to make sure that we don't end up like giving up things that we don't realize are really valuable and important until after we lose them, right? Because it really is easy to make like short-term compromises that say like, oh, we're going to rely on one node being in a data center, and in exchange, like theoretically everyone can verify. But what that would then mean is like then the chain stops being able to function without data centers, right? So there's a lot, like it's important to, I think, in parallel to some of these discussions on like tactics also, and like the short term, and how also think about some of this like long-term strategy, figuring out like what actually will the end game of decentralization and scalability look like. And there's a lot of really amazing stuff that we can do, right? Like I think within a couple of years, we can get to a world where even nodes that are interacting with the chain through RPC are going to get like basically at least similar levels of verifiability, and not quite the same, but approaching like the kinds of levels of privacy that you would be able to get if you run a node yourself. But like we have to actually think through some of those things and do those kinds of things. And like to me, the goal of the long-term Ethereum roadmap is basically to figure out like what is the end state of all of these different structures that we really wish to see, right? Like basically approach the problem from the opposite end, right? It's like if you imagine you're like in a car and you're going from like let's say Paris to Berlin, you want to have like a part of your brain figuring out, okay, how do I get out of Paris? Till I get into the highway? So then you want to have another part starting to run and figure out, well, what actually is the realistic way to enter Berlin, right? And it's like a kind of similar thing here, right? Like where if we decide on the wrong destination, then we do risk locking ourselves into the wrong thing. We're risking also making a life for ourselves at the same time. And so, to me, this is actually a big part of the value of this longer term effort that Justin's been working on, and I'll leave to Justin to talk about as well, right? But in in general, like we're able to, I think, get something which is much more scalable and at the same time something which is very decentralized, very censorship resistant, also much more simple than today, and something that offers stronger guarantees than today. So maybe I'll leave it to Justin to expand on that a bit.
Yeah, sure. I guess simplicity is a good segue. Vitalik, you had this recent post on a lot of the advantages of simplicity. Our values, permissionlessness, robustness, neutrality, can really benefit from simplicity. Things like having high client diversity, having systems that are simple enough to be formally verified, having 100% uptime. All of these things really benefit from simplicity. And I guess another theme of research recently has been optimality. And when you combine the two, maybe we have a credible path towards ossification through optimality. Now, I guess the reason why I'm on this call is because, as some of you know, we've had this naming issue around the Beam trademark, and really what I want to make sure happens is that if we do change to something else, that it's a really strong meme. And one of the things that we realized is that there's maybe a bigger renaming opportunity for all of Ethereum as opposed to just the consensus layer, and basically double down on this idea of simplicity. So we have the three layers, or I should say sublayers of the L1, the CL, the DL, and the EL. And each of these layers can benefit from a refactor around becoming post-quantum secure, for example, for the CL and the DL, but also around snarkification. And the meme that we're, I guess, proposing today is a lean Ethereum. So there would be the lean consensus, the lean data layer, and the lean execution layer. And again, across all of these layers, at least for the end game, there will be huge opportunities to focus on simplicity and maximum robustness, which includes snark friendliness and post-quantum security. And being lean doesn't mean not being scalable. That's actually the opposite. So there's huge synergies between scaling the L1 and scaling a DA for rollups with being lean. And the basic idea, of course, is very simple. The validators that run on home internet connections and commodity hardware just verify snarks and verify dank sharding samples. So yeah, that's the proposal now, and I guess the goal of sharing it today is to do a bit of a temperature check.
Perfect. Thank you. We can talk about this as part of the general discussion in just a second, but I think before that, my understanding is Micah wanted to say a few words as like words of caution for the scaling effort. Micah, are you on?
Yeah, sure. Can you hear me?
Yes.
Words of caution is one way to put it. I think what I've been talking to a lot of people lately about the situation, and just to give a summary for those who don't follow me on Twitter, which I'm assuming is just about everybody here. Most of the discussion around scaling talks about staking nodes and block builders and how can we make them as performant as possible. The thing that I see missing in all this conversation is a discussion of the RPC providers. Currently, the RPC providers, there's like basically three companies: Infura, Alchemy, and QuickNode, probably a handful of more smaller ones. But it used to be that the RPC server was you as a user. So as a user, you want to use Ethereum. You double click the Ethereum executable and it runs in the background on your machine all the time. And when you want to interact with the network, you just talk to your computer. And you're on a peer-to-peer network, and it was a peer-to-peer system. We're moving more towards a federated system where the users are talking to one of a handful of service providers who are, providing service, and they make their money in one way or another. So some make it through, don't actually know how Infura makes their money, but QuickNode, for example, sells their services. The problem with this is that's much less censorship resistant than a peer-to-peer system. In a peer-to-peer system, as long as you can run the software and find one other person in the network that's willing to talk to you, you can participate in the network. In a federated system, you need to find one of the few people who provides like the RPC nodes that's willing to talk to you. And we've already seen that some of the RPC node providers, the companies that do this, do censor people, like actively. Like they censor everyone in Venezuela, everybody in Russia, everybody in Iran. Like if you're in one of those countries, you just can't use Ethereum through those providers. Now, luckily, we haven't run into a problem yet, I think, where every centralized provider has censored. And so we haven't hit this yet, but it's not out of the realm of possibility. And so as I talk to people about this problem, I've come to realize that I think the core issue, which I don't have a solution to, is that there's disagreement among the core devs as to whether we should prioritize, when we have to make a decision, do we prioritize censorship resistance of the system, or do we prioritize scaling of the system? And sometimes you can do both, and that's great, and we can. But oftentimes you have to make a choice between censorship resistance or scaling. Sacrifice a little bit of censorship resistance, centralize the system a little bit more, and you get a lot more scale out of it. And it's, if your goal is to scale the system and reach as many people as possible, then it's an easy choice. You just scale the system and sacrifice a little bit of CR. I don't think this has always been the case with core devs. I mean, maybe I'm misremembering history, but I think back when I got into Ethereum, the core devs mostly prioritized censorship resistance. And that has been shifting, like this ethos has been shifting within the core dev community. And this, I think, is what leads to the disagreement as to whether or not we should even have users be able to run RPC nodes themselves. Like, there are many people who now believe, core devs and users alike, who think that it is not worth it to have a system where users can actually run their own nodes and have their own data. And some other people in the ecosystem, of course, think the opposite. They think that users should be able to run a node on their computer and have peer-to-peer access, not have to trust third parties, not have to dox themselves to third parties, not have to tell other people what they're doing. It's all locally available. So I would like to, I don't have a solution to this problem, the ethos misalignment problem. I think until everybody agrees on which one we want to have, do we want to prioritize censorship resistance, or do we want to prioritize scaling? Until there's agreement on that, I think we're constantly going to be butting heads on what the right solutions for any of these things are. I don't have a solution to this problem. If anyone does, that'd be great. If someone can figure out how to, in a decentralized development community, how do you align ethos? No idea. I think that's basically my pitch. Happy to talk more about it with anybody, anytime.
Perfect. Thank you. Yeah, then we're basically at the end of all the prepared remarks and presentations. So now I would open it up for this general discussion, either to what Micah just said or general kind of topics that came up on the call. And then we can wrap it up in the next 10 minutes or so. Where people are thinking about what they want to say, and just raise your hand if you want to say something. I just wanted to briefly address some of what you just said, Micah. I personally think that it's a false dichotomy between some of, like, basically the values of Ethereum and scaling. I personally think that at the limit, at some point, you do run into this trade-off, but we are very, very far away from the efficient limit right now in Ethereum. And the challenge right now is much more to just like make things legible, because once you make them legible, you can track them and you can make sure they are in a healthy range. So for example, on censorship resistance, I think when we talk about this, we mostly talk, what we mean is mostly the censorship-free inclusion of transactions on Ethereum. And there we have looked into this, we've researched this, and with solutions like Fossil, we know that there are ways where we can ensure much better guarantees than we have today, while actually being able to have much higher scale and basically rely much less on, say, every proposer being able to build their own blocks at home, right? So basically there we can have the best of both worlds. And we got there just by making it legible, making it something we track and we find a solution for, and then we were able to find that solution. I think what you're pointing out here is good, is saying, okay, look, censorship resistance also means having access to state. And as we make it so that not everyone has their own Ethereum node locally, and state, and also like the simulated results of transaction execution, right? So ETH calls. That's just another thing that like I think it's good to raise, so we track it, but like treating it a priori as this dichotomy of like we have to choose between that and scale, I just don't think it's right. I think we can basically, we just have to make sure we track it. And then I don't think like these things, we already have sketches for how to address them. So yeah, so my feeling is in the past, we never had the ambition to scale. And so we just got all of these things for free with the existing solutions. Now, as we want to scale, we just have to make sure we work for keeping or even improving these as we go. But I don't think these things are fundamental challenges. Yeah, Vitalik?
Actually, I wanted to ask a question to either Mike or whoever else knows. Like, do we know what is the reason why the RPC market has been consolidating so much recently?
So I can speak to myself and the other people I know who have been users of Ethereum for like 5 or 10 years, who used to run their own nodes on their local hardware, and it's always the disk usage. Like everybody I talked to who used to run their own node on their desktop, they got to the point where it consumed more of their disk, and they were like, I don't care enough to go buy hardware just so I can participate in Ethereum. Just like people rarely go buy hardware so they can torrent, or rarely go buy hardware so they can watch Netflix. You know, they use whatever they have, and they just aren't willing to go to that extra step to go purchase hardware specifically for it. Even if the hardware is not terribly expensive, it's just that's the step that seems to stop a lot of people, is having to go specially build for Ethereum. The other minor one is operations. As someone who ran an Ethereum node on his desktop for a very long time, it is operationally challenging. At least it used to be. I haven't in a while for this disk reason. But that was the other reason that people started to fall off that I noticed, was that it's kind of a headache back in the day where your node kind of break randomly. You had to do these upgrades every 6 months. It wasn't something that you could just double click and ignore. So a counterexample of this is IPFS Desktop. I installed that on my OS, a year or two ago. It still runs. I never update it. It just works. It doesn't consume. I like when I run into bandwidth problems, it's not because of IPFS. When I run into disk problems, it's not because of IPFS. And I use it regularly. Like it's part of my daily workflow, but it's in the background. It's passive. There's no operational overhead, and there's no extra hardware for it. And this is a peer-to-peer decentralized system as a kind of comparison for what I think people are willing to run. Now, of course, this is a small sample size. It's just people I know who were Ethereum enthusiasts, let's say, historically. I don't know if that is meaningful in the grand scheme of things. That's obviously a different question.
Right. So one type of consolidation is like people moving from self-hosted to providers. The other type of consolidation I'd be really curious about is like going from 20 providers to having 3 providers, right? Because like having different options for providers and geo-decentralization of providers is another one of those things that's really important for the class of users that will inevitably exist and inevitably be large that are not running a node themselves. So I'd also be curious about like do we know what these markets or third-party hosted nodes looked like 5 years ago versus today, and has it gotten worse for these of the users? So like, was it always 3 companies and always will be 3 companies, and that's a big part of it. So relying on it is so dangerous.
My semi-educated guess is that a lot of these providers, like Infura, provide service for free, and it's getting more because the requirements to serve Ethereum go up, as they go up. That gets more and more expensive to provide for free. Also, applications. I don't know if anyone has looked at the network tab of your browser when you have Uniswap open. Applications are not nice to RPC providers at all. Like Uniswap is sending, a transaction or a request every second to make queries to the RPC backend RPC node, like for their swap stuff. And those are like, equivalent of 1 million gas transactions every second to an RPC node. And that's every user that has Uniswap open in the tab on their browser doing something. And so my partial guess is that there's just no incentive to do it. Like most users don't want to pay for it as long as Infura is providing it for free. The same reason. Why does no one pay for email services? Well, because you can get it for free from Google. And so one provider provides it for free, and then no one can compete with that from a pricing standpoint. And so no one joins the market because it's expensive to run these operations. And eventually you end up with that one provider providing it for free, and then they have completely dominated the market share, and users no longer have choice. And I don't know if there's a solution to that other than like forcing Infura to stop providing free services to everybody, but that also seems bad. Like I don't see a clear solution to that problem.
Got it. One other question that comes to mind, which is like a bit of a different tangent, is I wonder, like, are there things that we can learn from the open source AI world in like what a realistic but successful and meaningful self-hosting ecosystem would look like, and like what things succeed, what things fail, or the things that we can do to try to like learn from and emulate any successes that have happened there.
I worry a little bit. Sorry, go ahead, Ansgar.
No, I just want to say maybe this is a good point where like we do async follow on, just to not keep people for too long right now on the call synchronously. So maybe I would just like have one last round of asking whether there were any comments or questions around any other parts of the call. Otherwise, I think it's probably best to wrap up here now and then continue this async. But yeah, then I think it looks like no further comments because just because we're already 22 minutes over time, and I had announced a little bit that we run over, but I don't want to keep people for too long. So then I think it's best to end here. And as I said, preliminary date for the next call will be June 4th, and we will likely talk about ZK and statelessness. Details and a more detailed agenda will follow closer to the date as usual. Thank you all, and see you on the next call.
Bye-bye. See you.
Thank you. Bye.